Hello friends, thank you for watching this video. Today we are going to talk about EV battery pack cooling CFD simulation using Ansys Fluent. With the rapid development of electric vehicles, portable electronics and renewable energy storage system, the demand for efficient, safe and long-lasting batteries has significantly increased. One of the major challenges in the battery industry is the thermal management. During charging and discharging, batteries generate a lot of heat due to electrochemical reactions and the internal current resistance. If it is not controlled, then that excessive heat can lead to performance degradation, reduced lifespan, and in extreme cases, thermal runaway and safety hazards. To address these challenges, researchers and engineers are exploring phase change materials as an alternative and a creative solution for battery cooling. What is PCM? PCM is phase change material. These are the substances that can absorb, store, and release large amounts of thermal energy during the process of phase change. It mostly happens from solid to liquid. By utilizing the latent heat of fusion, PCMs maintain battery temperatures within a safe and optimal range without requiring active cooling systems such as pumps, compressors, or fans. Compared to conventional cooling methods, PCM-based thermal management offers advantages such as passive operation, energy efficiency, lightweight design, and enhanced safety. However, there are issues like low thermal conductivity, leakage, and long-term stability remain an important considerations for practical applications. So as a result, PCM-based battery cooling is emerging as a promising area of research and development, aiming at improving the thermal safety, reliability, and overall performance of next generation energy storage systems. In the EV industry, there are certain battery power grades. The first one is the high energy batteries. These are the energy grade batteries, and they are mainly designed to store and deliver a large amount of energy over a long period. The other category is high power batteries. This is also called power grade batteries, and they are designed to deliver high bursts of power quickly. The third type is the combination of above two, which is also called a medium grade, and the purpose of these type of batteries is to provide a balance between power density and the energy density. And those are mostly used in plug-in hybrids, drones and industrial equipment. Batteries usually generate heat during the charging and discharging cycles, mainly due to the electrochemical reactions and internal resistance. So this heat must be managed to ensure safety, performance and lifespan. There are two types of sources of heat in the batteries. First one is Joule heating, which is caused by the internal resistance and the current, which is defined by the Ohm's law. The second one is the reaction heat, which is produced due to the electrochemical reactions and entropy changes. So the total heat generation is the summation of these two factors. So effective battery thermal management systems like liquid cooling, air cooling, or PCM based cooling are essential to dissipate this heat. This dissipated heat from the battery we're talking about is used as an input to the cooling CFD model for one of the battery load rating we are going to use in this simulation. This is going to be our battery pack model. On the left side, you are looking at the top view. These are through holes which represents the battery cells. This design is composed of two blocks. First is top block and there is a bottom block. Both of these are the PCM materials separated by adiabatic walls. This means they cannot transfer heat to each other. On the right you can see the cut section of the same, how those blocks are split into two. Let's look at the simulation conditions that we are going to use. The cylinders you are looking at are the EV cells. So we are going to apply a heat source on those cylinders. The top and bottom block are made up of a PCM material, and the walls that separates the top and bottom block are adiabatic walls, and there will be a gravity in the direction as shown. A battery pack with the two blocks of PCM is chosen here to demonstrate the simulation process. The PCM material we are going to use is paraffin wax, and the properties of the material are as below. The properties are shown at two temperatures here, 48 degrees Celsius and 62 degrees Celsius. These are the liquidus and solidus temperatures. So 48 degrees Celsius is the solidus temperature and 62 degrees Celsius is the liquidus temperature. That means at a temperature of 62 and more, the wax will be in the liquid state. And similarly, the temperature of 48 and below, it will be in the solid state. And the latent heat of fusion during the process of melting is 180 kilojoule per kg. A battery heat load will be applied on the cylindrical surface as we talked about. This is the simulation process that we are going to follow for this simulation. We're going to start off with the geometry creation from the scratch. So geometry will be created in Ansys Space Claim Direct Modeler. Mesh will be generated in Ansys Workbench Meshing tool. We'll set up and solve the problem in Ansys Fluent along with the post-processing of the results. Let's get started. So we're going to start off with creating the geometry first. Let's create the whole block first. I have drawn a random rectangle here, and then I'm going to constrain it with some dimensions. We are going to change these dimensions later. We are constraining these dimensions with respect to the axis. As you might have seen, I was clicking the axis first and then the lines. So that way, the lines will move when we change the dimensions. As you have seen, we have updated the dimensions, and you might have noticed the outer edges were moving with respect to the axis. Now let's create the circles to create the tubes. Let's create a construction line at the center. Please remember, this construction line is just for constructing the geometries. It will not be a part of the sketch, and it will not be used for extruding or creating the 3D geometries. This is just for referencing purpose. So let me create the first circle on this line. The diameter of the circles is 18 mm, and it is at a distance of 13 millimeter. Looks like it is exactly 13 millimeter. The next circles are going to be at equal distance from the first one. So let's create a copy of those. We can select move, select circle. If you want to make a copy of any entity while using a move operation, then you need to hold the control key. For that operation. For example, I am holding the control key and going to move this 26 mm. Now you can see it is exactly at the center. I can do the same thing with this circle. Hold the control key and move the arrow and then press the space bar. Once you press the space bar, now we can create the copy of the second one. Let's select the second circle and do the same operation. Now we got three circles. One row is completed. Now we need to create two such rows, one above and one below. Let's use the move option one more time, but this time we're going to select all three circles. Use the control button to click all the three circles and do the same operation. Hold the control key and move the arrow. Press the space bar and enter 26 millimeter. You will see the copy of the first row is generated. Now time to create the bottom row. Once the sketch is complete, we can go to the 3D mode. Now you can see that the sketch has created this surface. Now we just need to extrude this for the height. So we are going to use the pull operation and extrude this surface in this direction for a height of 65 millimeters. So we have created our block. Now it's time to split this block into two. In order to do this, let's create a plane at the central section of this block. So I am going to pick two opposite faces and select a plane option. This will create a plane at a center distance between these two surfaces. You can see now the plane is created exactly at the center. Now we are going to create one sketch on this plane. So let's select this plane and go to the sketch mode. Let's align the view. Now the splitting is going to happen at the center plane. So let's create a construction line. But before that, let's project the model edges on the sketch by just clicking the background model. Once you use this option, the edges of the background model will be projected onto the sketch, and those edges can be used in the current sketch. So we are going to create a construction line exactly at the center. Once you hover your mouse on the line, you will see a triangle. So triangle denotes a midpoint. So you can click there and connect it to the triangle of the opposite edge. Now let's zoom on to the area and let's create a splitting line from here first. And I'll create one more line, the same line like this, and another line that's going to be connected to this line. Now, as we have created these edges using the reference edges from the background model and the construction line, we don't need them anymore. So we can get rid of those. You can just select here, click the lines and hit delete. It will delete. Similarly, do the same for these lines. So these lines form our cutting surface. But this is not complete yet. We need to close this in order to create a surface. So create a line to close this loop. Once the sketch is complete, we can go out of the sketch to the 3D mode. You can see this, the surface is created. Now we are going to use this surface to extrude a 3D and then later use this as a cutting tool for the block. So in order to extrude this, we can use a pull option. In this option, we can use this option which is called pull both sides because we need to pull on either sides of the surface. So you can see once we click this, the arrow has changed to both sides. There is one important thing that we need to do at this stage before using the pull operation. You can see a no merge operation. So before doing any pull operation, try to select this option so that the new solid that is going to be created should not be automatically merged into the earlier bodies. Let's extrude this for the length just slightly more than the block. As you can see, the two separate solids are created because you use this option. If you don't use this option, there will be just one solid. Now as there are two solids, we can use one to split another. In order to do this, we can use a combine option. This combine option is used for subtracting one body from another in addition to merging the bodies. So let's try the subtraction operation. So first select the box and then we need to select the cutting body. This is the cutting body. But before you click that, let's uncheck this option. So because we don't need the cutter here, we just need the split box. As you can see, our main block is now divided into two blocks and the cutter solid is gone because we had unchecked this option. Let's hover the mouse over the structure tree. You can see this is the bottom block and this is the top block. Let's name those. Let's name those as this is a bottom block. So our geometry is complete. Now let's go for the next step. But before we go for the meshing, we need to do couple of more steps because there are two solids here. Let's look at those. First, let's create the name selections. In order to name the adiabatic walls, we can hide this block to get a better look at the adiabatic walls. So these walls are going to be adiabatic walls. So select these walls, go to groups and select this button. So we can name those as walls adiabatic. Let's show all the blocks. Now we need to name the cylinders because we are going to apply heat source for these walls. But let's do one thing because these are two different solids. Let's name the cylinders of the top solids different and the cylinders of bottom solids as different. You can just hide the other part. Let's now name all the outside faces of the block. Let's now save this file. Now before we go to the next step, we need to do one last step in space claim. It is called share topology. Once you click this, you can see the surface which is common between the two blocks are highlighted. We need to do this step in order to create a conformal mesh between the two blocks. Once done, we can save this file. Now let's open the workbench and drag and drop the mesh cell. We can now import the geometry which we have created. Let's go to the working directory and read the space claim file. Once the geometry is loaded, we can now open the mesh cell. This is the meshing software. You can see the two volumes that we had created and given the names. Let's assign the category of the volume as fluid for both the solids. Now let's do the mesh settings. Please keep in mind that this video is created for the Ansys Fluent student version. This version has limitations in terms of the max number of elements that we can use. So considering that, we have chosen the sizes accordingly. In this case, we are going to use a tetrahedral mesh in both the volumes. So let's set it up as a tetrahedron. Now let's give some sizings. We are going to use a curvature sizing function for the cylinders. We can select all the cylinders using a box select mode. Let's do some trials with the sizings and let's generate the mesh. This is the mesh that is generated. Let's take a closer look at it. This is the total number of elements that are generated. And let's look at the quality. For tetrahedron mesh, the mesh parameter for quality is skewness. The skewness should be under 0.9. A good quality mesh is now generated. However, it can look a little bit coarser. We can always refine this by changing the sizes. Let's do some trial with the sizes. For mesh independent study, we can always go on reducing the sizes and look at the effect on results. The maximum quality is within 0.9 and we are within the limited restrictions for mesh elements. These are the names we had provided in space claim to different surfaces. Now let's export this mesh for Fluent. The mesh extension here will be .msh. Let's save the workbench file as well. You can always reopen this workbench file to do some changes in the mesh. We can close this workbench session and also the meshing session. Let's open Fluent. Once open, we can now read the mesh file which we exported from Ansys Workbench. Let's go to the working directory and read the .msh file. Now we are ready to do the Fluent case setup. Let's look at the mesh details and the domain details. It is always good to ensure that the units are correct and the domain sizing is correct. For the physics, for the turbulence model, let's check laminar for this case and also check the energy because we are going to solve temperatures. Next comes the solidification model. Let's switch on the solidification model and leave everything as default. Let's now add the material that we need for this simulation. By default, the material is air. We can replace this material by paraffin wax. Before changing the properties, let's change the units of temperature to Celsius. This is just for the convenience to enter the temperature values. We are going to use piecewise linear profiles for density, Cp, thermal conductivity and viscosity for the temperature variation. Our profile has 4 data points. Let's define those points as shown. You would notice that as we change the units to Celsius for temperature, we can now enter the values of temperature in that unit. Once you define all 4 points, the graph will be updated. Before moving forward, we should always verify if the data displayed is correct. In addition to above properties, we need to input the melting heat, that is heat of fusion, the liquidus and solidus temperature. We can click change or create to save these properties. We need to now assign this material for both the PCM blocks in our model. We can also change the name of the fluid zones to make it shorter and easier to identify. It's now time to set up the boundary conditions. For cylinders, we are going to apply a constant heat flux value. And for adiabatic walls, heat flux will be set as 0. Gravity is acting in negative y direction in this case. Let's set it up accordingly. Let's now set up the solver and control settings as shown. We also need to switch on the time mode as transient because we are going to do the calculations with the physical time. The solver part is done here. Let's now define some monitors to track the different variables with time while the case is being solved. We're going to set a volume average variable in this case for liquid fraction of the PCM material. We can select both the blocks together for monitoring. Please make sure to switch on the per zone option here. This will monitor the data of both blocks in a single window. Please also make sure to enable the report file option if not already enabled. This will save the monitor files in your working directory. Now we are going to track the temperature of battery cylinders. This is going to be a surface monitor. Rest of the setup of temperature monitor will be same like a volume average monitor. We can now initialize the case with the temperature of 25 degrees Celsius. This will be our simulation starting physical time. Next we can do some setup for animation. For this we need to create a plane to monitor the different values on. Let's display the mesh. We can look for the coordinate for this plane. Based on the view looks like it will be a constant z plane which will be at the midsection. Let's create this plane. We can always display this plane to verify the location. Once the plane is created, we can now set up the contours. We are going to use these two contours for animations. One contour will be for temperature and another one for PCM liquid fraction. Let's do some color map settings so that the picture saved will be properly readable and of good quality. We can preview the pictures that will be saved during the simulation. Once satisfied with the pictures, we need to set this up as a view and save it. This will be used later in the animations. Let's set up the liquid fraction contour similarly. We are now good to go to the setup of animations. Please do the settings as shown. The animation file name and frequency of frame saving are the personal preferences. As a final step, let's define the simulation file's auto-saving frequency. It is always important to save these files at intermediate times. Our setup is complete now. Before starting the run, please don't forget to save this file as the initial file. This is always a good practice to have an initial setup file. We are now good to go for calculating the solution. Let's provide the time step size and the number of time steps. 20 sub iterations should be enough for this simulation. We can click calculate. You can see in this window that there are graphs of both the blocks that will be updated. Animation frames are also updated at every time span interval we had specified. This is the final result after completion of those time steps. These are the graphs. Let's look at the animations. We can play the animations from here. Or later we can use the right option to save the animation video file to our working directory. Let's look at how to process those monitors we had saved. We can do that in an Excel file. In Excel file, go to Data Import and import the data from text or CSV option. We can then read this monitor file. This will be a .out extension file. We can locate that in our working directory. Once read, we'll need to split the columns. This process can be different depending on the version of Excel file. Hence, please proceed accordingly. We can see here that the columns are separated and it has the data of a respective variable for both the blocks. First column is for the time step number, which we do not need for these calculations. We can delete this column. In my Excel version, when imported like this, the data does not appear as number category. Hence, I am doing this as an additional step to convert the data type of these values as numbers. You may or may not need to do this. I selected all the data and clicked an option called Convert to Number. We are now good to create the graphs as usual. We can see in this graph that the top block PCM material melting starts a little later, but catches up with the bottom block with time. You can import and plot the similar graphs for temperature data as well using the temperature monitor. This concludes the session on CFD analysis of EV battery backup cooling. Thanks again for watching this video.